a silly way to remember the diatomic elements on the very bottom of this How Do Elements Exist sheet called Hunkelbrief, which Hunkelbrief means absolutely nothing other than it's a mnemonic device to try to remember which nonmetals don't exist just as O, but instead O2. Again, our atmosphere is primarily oxygen and nitrogen gas, but oxygen itself is too reactive, has a really high electronegativity, to just exist as a single atom of oxygen floating around other single atoms of oxygen. They'll instead bond to another one, or in nitrogen, N2, hydrogen gas, H2. So we have these diatomic elements that's introduced in this sheet. Again, metals can exist on their own. You can cut a metal in half, cut it in half, cut it in half, and you can get to the point where it's a single atom of a metal. But you can't get that way with some of the nonmetals. Now, some nonmetals, like the noble gases, sure, they exist on their own. But what we are trying to do, and partly why you ended with a little bit dealing with alloys on that activity that you just did in the lab benches, is to show you how these things exist. How do we use these different elements in our day-to-day life? Now, our body uses the oxygen in our day-to-day life. That allows us to live because we have to breathe that in. But we need to have a better understanding about how these exist. And part of that deals with how do they hold together within compounds. So what we're going to do is, if you can get out your notebook, we're going to take a little bit of notes to go over these different bond types. So we start with that How Do Elements Exist sheet, just to have you get a little background in how do these things come up. But now I want to move in then specifically into the different bond types. So in our notes, we are going to review ionic bonding. We've talked about it last unit. We've used it early in this unit. We're going to review metallic bonding, which was a little bit of the last couple of class periods. But I have to introduce a third type of bonding called covalent bonding as well. So that's kind of our goal with the notes here. So first off, if you find that a lot of this stuff in this first slide is just review and you don't want to write it down, feel free not to. Quite frankly, the last time you took notes, if you keep an order, you might have written this down recently. An ionic bond is typically between a metal and a nonmetal. I say typically because there are a couple exceptions that we will show you in the coming weeks. Remember, sometimes we refer to it as a cation and an anion. How an ionic bond works is the cation transfers electrons to the other thing, the anion. So the metal gives to the nonmetal, making a positive and a negative ion. Just as you saw in the activity at the lab benches, what holds these things together then is they have opposite charged particles. Na plus, Cl minus. That is the simplest example of an ionic compound. Perhaps even in notes or talking about ionic compounds, I might have brought in a little bit of biology terminology of a symbiotic relationship where Na and Cl can work together to reach a common goal. Na loses the electron, that's good for Na. Chlorine gains the electron, that's good for chlorine. They work together. And we'll remind you of that octet rule on the very last slide after I go over these different bond types. I have an animation that goes over this. It goes kind of fast. If you pay attention to the Na on the left-hand side, it starts with one valence electron. Remember, valence is the fancy chemistry term for outer. As it gets closer to chlorine, chlorine can attract that electron. It pulls it in. Recall from last unit, the ability to attract another element's electrons is called electronegativity. Chlorine has a high electronegativity. It's good at gaining electrons. Sodium has a low ionization energy. Ionization energy is how easy it is to lose an electron. Now, unfortunately, it's hard for me to pause this video to kind of show you that there's chlorine starts with 7 electrons around it, but you can definitely notice that it has kind of an opening as it's spinning around. And then that sodium electron fills that opening. Whoever made this animation, they're trying to show the fact that electrons aren't stationary. That's why they're moving around constantly. It does make it a little bit more difficult to kind of see at any given moment, though. We could draw a Lewis dot for these by showing stationary dots around the chlorine. But now the sodium is at the octet. It's like neon. It lost an electron in its 8 outer shell electrons. Chlorine's at the octet, like argon. It gained an electron. So this is hopefully all review of what we've covered before. Kinsey, were you able to draw this animation in your notes? You could kind of flip book it or something. All right, metallic bonding. This is what we've been covering a little bit here or there the last couple of class periods. And as the video that I showed you at the start of class references, we often refer to it as a sea of electrons. You saw it in the cutout activity that basically you have a positive nucleus and you see a negative electrons in between the two. That's what's holding them together. I can relate this back to the trends of the periodic table just like I did with ionic. Metals have low electronegativities. That means they are not good at taking electrons from a neighbor. They don't hold on to their own electrons very well. They have low ionization energies. Then I showed you an animation or a video that kind of referenced ping pong and the balls bouncing back and forth. I kind of like the visual of playing hot potato with a whole bunch of people where what's keeping everybody together is the game of passing that hot potato back and forth. However, no one wants to have that in their hands, so it's constantly bouncing around. But what holds a metal together is the fact that it's no longer 2 elements attracted to one another by opposite charge. It's usually the same element, and they're all just attracted to the negative electrons floating within. Again, a lot of the properties of what makes metals important is due to those sea of electrons. Electricity is just a flow of electrons. Metals are usually used to conduct electricity because their electrons are not held in place. In that previous slide when I showed you that animation, chlorine holds those electrons around it. Those electrons are not floating from point A to point B. However, in a metal, they are able to do that. So that's why they're good conductors. Because these electrons can move about, that allows like electricity to flow in a wire, heat to be transferred from one end to the other. Again, if you are stirring things with a metal spoon that's in a hot pot, your handle of your metal spoon is, or your wooden spoon is just fine. But if you use a metal spoon, the handle could get hot because it can conduct heat. Again, metals can be bent into shape, as that activity showed you, unless we sprinkle in another element to make it an alloy, like that steel example that we had at the lab benches. The good news with metallic bonding is 2 parts. One, since metals typically exist on their own, there is no special naming for just metallic bonding. We went over naming for ionic bonding, and as you can see up on the board, we're going to go over naming for covalent bonding, the next bond type I have to go over. But metals themselves, if you have a whole bunch of nickel just all together, it's just called nickel. There's no special name for it. So that's good news number 1. Good news number 2 is because these electrons are constantly floating around, we can't do Lewis dot for it either. So we need you to know the 3 bond types. I like relating the trends of the periodic table to them, in particular electronegativity. But then there are skills things that we do in this class. So understanding the difference between bond type, that's important. But then the skill of doing Lewis dot, the skill of doing naming, well, we don't have to worry about that for metallic bonding. So that's the good news for you there. This brings us to the last bond type that we have to go over, which is called a covalent bond. if an ionic is between a metal and a nonmetal, if a metallic bond is between two metals, a covalent bond is between two nonmetals. And a covalent bond is more of what we would call a true bond. An ionic bond isn't so much a bond, it's just opposite charged particles attracted to one another. A metallic bond is just positive nuclei, negative electrons. But what you're going to see is that a covalent bond is more about sharing electrons. Now, covalent gets a little tricky. Ionic bonding is the easiest type of bonding. That's why we go over that first. Then it's good to compare ionic to metallic. That's why we did that second. Covalent gets a little dicey. There are two types of covalence. One's called polar covalent, one's called nonpolar covalent. And once again, this is all based upon a trend that we covered last unit, electronegativity. If you do not need the definition of electronegativity because you already know it, you can ignore this bullet point. Otherwise, a reminder, what is electronegativity? It's when an atom pulls on electrons from a neighbor. And in parentheses at the end of the definition of electronegativity, I remind you that this pull comes from the positive nucleus. Last unit, we would have learned that fluorine has the highest electronegativity of any element on the periodic table. It's in the upper right-hand corner. It's really good at taking electrons. However, in an ionic compound, the metal loses an electron to the nonmetal. Both are, quote-unquote, happy. If a nonmetal isn't near a metal, it has to find another way to get to that octet. And that other way is through a covalent bond, through sharing of electrons. The last thing I have on this slide, and I'm abbreviating electronegativity EN, this is something that we're going to cover a little bit more in the coming class periods, is that we are going to look at these electronegativity values of different elements. If the electronegativity of the two bonded elements is a very small difference, you're going to learn that that's called a nonpolar covalent bond. If there's kind of a medium difference in electronegativity, we're going to call it a polar covalent bond. Actually, if there's a high difference in electronegativity, I didn't include this on the slide, but that would be an ionic bond. Our focus today will not be on polar versus nonpolar. However, I wanted just to get all the note-taking aspect out of the way. So I wanted to cover notes completely today, so I wanted to introduce this topic to you, which we will cover more in coming class periods. I think what's more important is the first two bullet points for right now. How do I identify a covalent bond? Two nonmetals, two different nonmetals coming together. Actually, those diatomics that I started off with, those are two nonmetals. So when we say O2 is what we breathe, that's two individual oxygen atoms covalently bonded together. What does that covalent bond mean? It means it's a sharing of electrons. And just like with ionic, I found a little animation for it. I found a little animation for covalent as well. So we can take a break from writing and just look up at the screen. So again, it will start over, although it doesn't say instant replay like the last one did. Notice how I have two individual atoms bouncing around. Again, if you focus on one of them, the start, they have 7 outer electrons. The golden rule of stability is 8 outer electrons, the octet rule. Now, if these are two things, both with 7 outer electrons, it's not like one of them is going to take one for the team and just give its electron to the other one and become more unstable while the other one becomes stable. And atoms don't have thoughts or feelings. What they do have is electronegativity and ionization energy. How good are they at losing electrons? Ionization energy. How good are they at gaining electrons? Electronegativity. If we have two things with 7 outer electrons, odds are they have a high electronegativity. They're good at gaining electrons. What will happen is the two will share, and you'll see that locking up, that sharing, and that's what holds them together. Because now that green nucleus is not only attracted to its 7 electrons, but to that 8th electron from the neighbor. This kind of overlapping of orbitals where one electron is attracted to 2 different nuclei, that is what a covalent bond is. It is hard for us to draw out, so next class we will introduce Lewis dot notation for covalent instead. But when we talk about sharing of electrons, that's what we're referring to. And again, my last slide is reminding you of that kind of golden rule of stability in chemistry, the octet rule. Having 8 outer shell electrons, I spelled noble wrong, it should be N-O-B-L-E, sorry about that. Nobel is the prize, that's a little different. 8 outer shell electrons ending in an S2P6 makes you stable. Ionic compounds. The metals will lose electrons to get to the octet, the nonmetals will gain electrons to get to the octet. An example, sodium in NaCl loses 1 electron. It loses at 3s1. And in doing so, it now ends in 2s2, 2p6, has a full outer shell 8. And I could show the same thing with chlorine. Chlorine gains an electron. But in an ionic compound, you have gain and loss working side by side. In a covalent, however, they share electrons. Take, for example, oxygen. Oxygen has 6 outer shell electrons. If we think about water, water is H2O. 2 hydrogens, 1 oxygen. Hydrogen's a nonmetal, oxygen's a nonmetal. The reason why the formula for water is H2O is that if oxygen shares 2 electrons with hydrogen, which that means you have to have 2 hydrogens because each hydrogen only has 1 electron, it too can get at the octet. So the goal of notes was to kind of review ionic, and if we're, maybe it was more than a review for some of us, review metallic, which was a little bit more recent, but then introduce covalent bonding, this last major bullet point here. Because how elements get to the octet in covalent is very different than ionic. Our focus for the next few class periods is going to be more on covalent than any other ones. Although, as I mentioned at the start of class, ionic compounds are still very important in the laboratory. So we go over ionic a fair amount still coming up. To be honest with you, metallic is something that we don't cover nearly as much because it doesn't have as many laboratory applications for us in this class. What I'd like to do when you get done with this is have you have 2 different sheets of paper. One of them is titled Nomenclature Using Greek Prefixes. In other words, this is our next type of naming that we're going to go over right now. The other one is titled Polyatomic Ions in a Few Odd Bits. So if you can have both sheets out, please. we are going to go over covalent naming today. Two different things to go over with covalent naming. First off, remember these diatomic elements. Before notes started, I had you read the sheet of how the elements came about. If it is a nonmetal bonded to itself, like O2, one oxygen bonded to another, N2, one nitrogen bonded to another, we just call it by its element name. Oxygen is O2, hydrogen is H2, nitrogen is N2. So we have to get used to the fact that when we reference these things, when we say oxygen, there's no such thing as one oxygen atom existing on its own. It's too reactive. So it's O2, that would just be called oxygen. Now, what we have to go over today is what about compounds that are two different elements bonded together? For example, NO2 is nitrogen and oxygen bonded together. So there's a new type of naming that we have to do with that. Because this is two nonmetals, this is covalent naming. First, if you are looking at the sheet that was titled Nomenclature Using Greek Prefixes, on the top it says binary nonmetal compounds are named using Greek prefixes found on your polyatomic ion sheet. Let's look at that polyatomic ion sheet. There's a lot of stuff on there that we're going to be covering over the course of the next week and a half. I want you to go to the very, very, very bottom of the sheet where it says Greek prefixes. And how about right where it says Greek prefixes, you write down on this sheet covalent naming. So again, you should see on this sheet on the very bottom a 1 it says mono, a 2 it says di, a 3 it says tri. On the very bottom left-hand corner, why don't you write down covalent naming? So you know, for this sheet that has a lot of information that we're using the next couple of weeks, you only need to use this bottom part for the next couple of class periods. I would also keep this sheet near your periodic table. As you're writing that down, if I look at that how-to sheet again for using Greek prefixes, it says the rules. Use the prefix to let your reader know how many of each atom are found in a compound. For the first element in the compound, you only use a prefix if you have more than one atom. And then finally, rule number 3, eliminate double vowels. In other words, CO is referred to as carbon monoxide, not carbon monoxide. Just a couple examples given to you as well. Ladies and gentlemen, quite frankly, covalent naming is the easiest naming that we go over all year. The problem with it is you can only use it when you are naming non-metal bonding, covalent bonding. So when I look at NO2, if I were to name this, well, the name of N is just nitrogen. O2 means I have 2 oxygens. When you have more than one of an element, you need to look at that Greek prefix table. Di is the prefix for 2, and then oxygen, we still make it end in an I to show it's bonded to something else. NO2 is nitrogen dioxide. Next one, N2O5. Here, there is more than one nitrogen. So we need to use the prefix to say how many there is. Dinitrogen. Prefix for 5 is penta. But since oxygen begins with a vowel, we'll just call it pentoxide. How about you right now, using this sheet with the Greek prefixes, do the left-hand column where you are going to give the written name of those last 3 formulas. Again, if there's more than one of it, you have to use a prefix to represent how many there is. And then do the right-hand side. Here's the written name, write out the formula. You guys take a few minutes to do this, and we'll go over together as class.